So this is going to be a little more of a flyover than a step-by-step freshman lecture, which was beautiful, Dan. So just like Dan did, although it said sequence comparison, he spent quite a bit of time just talking about one sequence. So I'm going to do that too. Maybe and almost everything I'm going to say works for Markov chains, but that's more complicated. Just like Dan, let's talk about PAT just to mean a pattern. So we're going to look for that PAT in this sequence, thinking, as my advisor said, thinking probability. So immediately I come to something. How are we going to count the pattern we see? And the general distinction is, are you going to count all the occurrences of PAT in that sequence, or all the non-overlapping occurrences? I spend most of my time not talking about non-overlapping, so I thought I would bring it in right here at the beginning. Let's take the pattern to be, let's be heads and tails. And so let's take that pattern. And this non-overlapping counts. Go along until you find the pattern, and then you start over again. The last letter, you mark it, and then you begin as if you were beginning at the beginning of the sequence. And one of the objects of interest is what's the difference, or excuse me, what's the average amount of time between these non-overlapping occurrences. Eraser somewhere.
That funny thing.
It's on the wall, is that it?
Yeah.
Oh, all right.
It looks like a mouse.
Wait. Okay. So let's do this. I'll just take this guy here. Now this guy overlaps itself, of course. And H, T, H, T, H. So there's different ways. So we have HT, HT, H in the text. So it may have occurred, for example, the pattern could have occurred before this. So we'll do U, we'll make this position N. So you could have had the pattern occurring here, this being the end of the pattern, then you would have had to have two heads and two tails, where P is the probability of heads and T is the probability of tails. Or this could have been the first time you saw it, it's hidden here, and then you would have had to fill in a PQ, or this would be the first guy you got. And there's a theorem in renewal theory that asymptotically, these become like 1 over the waiting time between the occurrences. So why was I doing this? I was doing this because this pattern occurs with probability PQ cubed squared. That's an equation any of us can solve, and you see it's got in it the overlap information. So you would solve for mu being equal to 1, I'll do it this way, p squared q squared plus pq plus 1 over pq squared. So you'd expect the time until you get to the next occurrence of this to be 1 over its probability. This, because you trimmed those guys off, you've made longer spacings. So if the P and Q were a half, it was fair coins, this guy occurs with frequency 1/32. But this makes that, I've got this is wrong here, this is P cubed. So this says if you do this non-overlapping counts, you push the spacing farther apart. So if there were 5 heads in a row, and then we'll take another pattern, so there's no self-overlap to this pattern. These guys have the same probability, but this one occurs in clumps. You'll get this pattern, and then with probably a half, you get an overlapping one, and then another overlapping one, and then a longer space. So even when you're counting overlapping patterns, this guy has a much higher variance than this one. So if you do naive using binomials to compute statistical significance, it's a classical mistake people made. So I'm not going to talk, for here on, I'm going to talk about allow overlapping counts. But I wanted to start there. It's somewhere. Okay, so I'm going to go through a couple of things Dan talked about, global alignment, local alignment, just to remind you of what that is, if you don't know. And then the main topic is the statistical distribution of these alignment scores. And I will show you a couple of very cool unsolved problems that I would love it if somebody did. So global alignment, which essentially Dan talked about, we've got 2 sequences. We want to relate each and every letter in an optimal way. And here we're allowing scores. So it's not just 0 or 1, but there's a score of pairs of letters in the alphabet. And for the dashes Dan was putting in, we're going to subtract a penalty. It might be 0, but we'll subtract a penalty. So this is alignment, just like Dan talked about, maximizing a score. So that's global alignment. And there's this dynamic programming algorithm, which you've basically seen without the scoring in it. And then there's local alignment. So in this problem, we're interested in pieces of the text that have the highest similarity score. So here you're going to have plus for stuff you like, minus for stuff you don't, and you're looking for the 2 intervals that have the highest score. And there's a similar algorithm that Temple Smith and I were lucky enough to stumble onto, where you essentially start the algorithm over in the middle of the table. If it has a negative score up to that point, you just put a 0 in and move on. And we said yesterday in the introduction, talked about problem formulation. And in, I think, 1978, introns were discovered. Nobody knew introns were there. And in bacteria, the genes start, they go along, they stop. And of course, that was going to be true with everything else. And then Sanger sequencing got going, and we discovered these crazy introns that were breaking up genes. And Temple and I certainly knew that our previous algorithms for global alignment would not work in these cases. But we had no idea what the problem was. We'd been given a properly stated problem. It would have taken us about 30 minutes to do it. Instead, it took us 2 years. So biology keeps coming up with bizarre things that make us work harder. So what's the statistics of sequence matching? There are some results for global alignment, but it's very tough, and I'll say something about that. We have some useful results. Local alignment has some very good strong laws of large numbers, some good distributional results, and I should just say that BLAST is a program looking for local alignment, incredibly more efficient than the dynamic programming algorithm of Smith and I. It efficiently finds local alignments, and it gives e-values or p-values for what's found. And the statistics are probably more important than the algorithmics in this. These papers, two of their papers, have been cited approximately 60,000 times each. So this is hugely used stuff. This is where I think computer science and statistics can take some credit for doing something useful to biologists. So what are we doing? So I talked about this before. We'll come back to statistical long matches. But how do we count the matches? And if we set 3 heads in a row we were interested in, there would be 3 runs of those here. And if we wanted to use the Poisson distribution to approximate rare runs, we would get it wrong. And what is properly approximated by the Poisson distribution are the number of clumps. So a tail followed by 3 heads. So the tail is what sort of declumps, and so you count the number of clusters of H's that are at least 3 long. So you can't directly apply this, and this has to do, of course, with the overlaps that I was talking about earlier. So you can't use the normal that you would get out of your first course, but there is a variance calculation that has to do with the self-overlap, and you get a central limit there. These are short ones. And in multivariate word counts, you have a set of words, more than one, and you want the multivariate normal approximation for the number of times word 1 occurs up to the number of times word m occurs. And these overlaps I was talking about, you could talk about the overlap between 2 different patterns, because they would influence one another for the dependencies. So there's a variance covariance matrix that you get from looking at the overlaps between and among this set of words, and you get kind of a classical central limit. This is for PhD students here. This was the thesis of Ron Lundstrom from Simon Tavare. Perfect PhD thesis. There was plenty of technical stuff to do. Surely it was going to work out. And Ron never published the result. But it's quite well known, and Haiyan Wang is in the audience here, did a Stein's method for rates of approximation of the convergence of these guys. It's pretty neat stuff. Classical looking. So what about this global alignment that I've been going about? So Dan's example was counting 1 for identical matches and 0 for everything else. And Schwadl and Sankoff in 1975 proved that the expected number of matchings was a constant times the length. That pretty much has to be, right? If you didn't do any alignment, you would get a linear growth in alignment score because either the letters would be identical or not. N times the probability they would be identical. And that was 1975. Many people have worked on this. No one can compute alpha, even for the example of a 2-letter alphabet and equally likely letters. No one knows. Now, if you take an example I gave you and you didn't do any alignment, it would be 1/2 times n for the expected number of guys. If you allow alignment, to show you how powerful alignment is, that you go from 0.5 to 0.82, you get a 0.32 increase over 0.5 by allowing dynamic programming to give you one of the optimal alignments. So your intuition about what's a good alignment score needs to be tempered by simulation and probability statistics for sure. Okay, so this is called the longest common subsequence. And there's something called ergodic theory, and there's a version of Kingman's subadded ergodic theorem, which in fact allows this, this conclusion to be made. That if you take the alignment score and you divide by n and take a limit, you will get a value. And it's just that we don't know what the value is. But probably everybody's heard of large deviations. There's something called Azuma hefting, which is a large deviations result. And what it allows us to do, so our expectation, the center of the distribution, is this constant times n. And we want to have more matching than would happen at random. So you would look at your random variable, subtract the mean, and say, what is stronger than that? And there's this exponential bound, large deviation bound, e to the minus constant times n, which looks absolutely great. And I had to write some survey paper for Journal of Royal Society. So I did simulations, thinking that maybe I would learn that Azuma hefting really gave practical values, and the upper bound on the p-values were 1. These sequences were just not long enough to allow this to, and again, while got these numbers. So cool. So and in that paper, I gave some plots, and I said, gee, the variance seems to be pretty much a straight line. And it was known before, due to Michael Steele, that there was an upper bound, something times n, that would bound the variance. And Slottle and Sankoff conjectured that the variance was little o n to the 2/3, which you may know. There's a famous result about the longest increasing subsequence of a random permutation. Very hard problem, but the exact distribution is known. And that's the variance they get. So Slottle and Sankoff were very smart guys. But it may be they were wrong in this case. Oh, and I also should say that when these results came out, I think Percy Diaconis, even in print, said that he was optimistic about obtaining the full distribution of the longest common subsequence. Because here there's a related problem with the solution. There's some work in the variance direction. A couple of papers have shown this proportional to n variance, but they're fairly contrived sequences. Their first example had, one symbol had extremely small probability of the two symbols. And they've increased this a little bit. The reason this is a hard problem is that there are a huge number of optimal alignments in this sort, and you can't get your hands on the statistical character of them as a whole. Whereas when we're talking about longest exact matchings and stuff, then we can get some angle. But I would love to see this established, and I would love to see the full treatment for longest common subsequence. This is probably not an important problem in biology, but it's a really cool problem. So let's switch to local alignment, and we'll just do it in coin tossing first. So we're going to toss coins, and what's the length of the longest run of heads? And the story I want to tell about this is the story of the Hungarian school teacher. So this guy, who I think taught high school, he he would take, we got a class. So this half of the class would sit down and dream up 200 tosses of a fair coin, and these people over here would actually toss a coin 200 times. Now, this is clearly, you couldn't do this with students in our high schools, but maybe in Hungary, people would work that hard. And shuffle them together, and this guy could, just glancing at the patterns, correctly classify them all. And of course, there are many tests for random numbers, right? But he was just boom, boom, boom. So what he was doing was realizing that the kids who were dreaming up coin tosses would not put enough head together. So it's almost guaranteed you'll have at least 5, and probably 6. You can do it. You can do the calculation and check me here. So anything, I think maybe it was 4. If they had 4 or more, he said they really tossed it, and less, they didn't toss it. And he got it right almost every time. I seem to have digressed in my talk here. Yeah, so here we are. So here's a trick of intuition, which if there's one thing you could take away from today, maybe this I love this. So let's look at the expected number of clumps of k-heads beginning with a tail, and we'll forget the end effects. So we have n places, a tail, and k-heads together. Now, the longest one is not going to occur too many times. Just imagine it occurred once. So you set this equal to 1 and solve for k. If you do solve for k, you will get essentially log base 1 over p of the length of the sequence. And this will sharpen it up a little bit. So that's where the numbers 5 and 6 come from, if you try that. A friend of mine who teaches probability in Sweden tells me, I give that heuristic to my students and they think it's a proof. Well, it's not a proof, but boy, it's a good angle to guess. So you have, essentially number of places to start times the probability of the pattern. Let me test you. So you have an n squared random zeros and ones on whatever biggest square with all ones. So how would you do that? What's the analog? I keep pushing this, I apologize. What's the analog of n times p? We had before n p to the k. That was essentially what was going on. So how many places can I start my square?
At n squared.
N squared. And if it's k, so there'd be p to the yes. And you set this equal to 1. And so this works in various settings when you're interested in the biggest one of some kind. So exact matching. P is the probability that the guys are equal, and we're interested in the longest, exact match with these random guys. And the law of large numbers is that when you divide the alignment score by this log 1 over p of n, you get 2, where, of course, 2 comes from tuition. And unlike Dan, I'm not going through the proof of this. It's something you can find easily and read. So there's that. Now, all biological sequences are not created equally, and this next material came from me asking Richard Aratia, what about two different distributions? How strong is this limit law? And what resulted was that there was a similar limit law, and of course the constant doesn't have to be 2 anymore, but it's between 1 and 2, depending on how far apart the distributions are. And that's what I expected. But in proving this, Richard came up with a characterization of definition of the constant and a characterization of it being 2, just like the sequences were from the same distribution, but they didn't have to be the same. So there's a characterization of when they're 2. And I wanted to say, okay, maybe it's what you expect, I guess. So I need the example to go through this. So here's an example. The AIs are heads and tails of probability 1/2, and the Bs are heads with probability theta and tails with probability 1 minus theta. And the reason we cooked up this silly example is the probability of 2 letters are equal is 1/2 times theta plus 1/2 times 1 minus theta, which you'll see is 1/2. So the base of the log in the limit law is the same everywhere. So I've got something to talk about. And astonishingly, this thing is 2 when theta goes from 0.11 to 0.89. It sticks at 2. So what we knew before we proved anything was that at theta equal 1/2, it was 2 log n, and at, say, theta equals 0, lost it. They're either all heads or all tails, so you're looking for the longest run of heads or tails, so you get the 1 log n. That was the first limit law, right? I hope I'm making sense here, that if theta is if theta is 0, then the sequence is all tails. The B sequence is all tails, so the longest matching with the A is the longest run of tails. And each tail is probably 1/2, so that's why we knew that was 1. So I expected this to look like this, but and this is very pencil line thin here. So this really wants to be 2 log n. It's very hard to scare it off of that. So these are robust results, is what I'm trying to say. Okay. And you can put in scoring, but then you have to be a little bit careful. This example, we're going to have no deletions at all, penalize it infinitely. And we have to have the expected score between 2 random letters be negative, but there are a pair of random letters that have positive score. So this is forcing it to usually, the local alignment algorithm would usually be zeros, but rarely there'll be a run and it'll get randomly some whatever it is, 2 log n. And the p changes from being the probability of coin tossing to the solution of some equation. So we know, with no indels, we know where the distribution is sitting. I refer to Chen Stein here, and probably will again. Well, Stein was a genius at the statistics department at Stanford. He wasn't the clearest writer I've ever seen, but amazing. And he had a completely new approach to central limit theorems, and his student Louis Chen did a similar approach to Poisson distributions as Louis Chen and Stein. And this begins to get challenging. But the score, the local alignment score, under the conditions before, this would be our center, and so what's the probability of exceeding the center by C? And it's 1 minus the probability that nothing does, which is the probability of 0 in the Poisson. So this is the parameter of the Poisson, so it's e to the minus that. So that's the intuition for this Poisson approximation for local alignment. And this isn't proved for all possible cases, but I want to go back and emphasize these e-values in BLAST are a version of this result. And I remember hearing David Lippman say that he thought that the statistics part of it, the ranking of what's found when people do searches, was probably the most important part of their contribution. These tens of thousands of citations. So in this local alignment scheme, we're going to count, we're going to do local alignment, we're going to count +1 when the letters are equal, we're going to subtract a positive number when they're not equal, and we'll subtract delta when there's a space that goes in. And we, of course, have the Kingman limit. But that's region right here. So this is proportional to alpha n scoring. Up here, where we're looking for exact matchings, this one is proportional to the logarithm of the sequence length. I'm assuming both the sequences are the same. What about in between? Good question. And what I expected was that there would be linear growth near 0, 0, logarithmic up here, and there'd be some mush in the middle. What turned out from a simulation was that it was log, proportional log, up to a line, and right at, got that wrong, proportional n, up to a 0 thickness, a genuine line, and then proportional to log n in the rest. Sharp phase transition between these results. And the line was defined, the line is simply finding where this limit, the expectation divided by the length, is 0. So of course, where it's positive, you're going to have linear growth. What about showing logarithmic up here? And it took Richard and I think 3 years or something to do this. And fortunately, the proof got much simpler with the Azuma hefting. You can almost read the proof now. So much less obviously algorithmically. And this is just, we're just talking strong law here. We're not talking about Poisson approximation yet. And so, but my conjecture is that Poisson approximation holds throughout this entire region. And while the full distribution for the Kingman type result is probably not important to biology, this is truly important for biology. And I hope someday somebody gets there. But it's probably, proving this is probably harder than so let's go back to counting number of words in a sequence. And I've just, this is a slide we saw before. We can't use the bioma directly, but we can mess it around and get normal approximation by taking into account the silicon. And this is this multivariate thing. So it's a little bit fits in with Dan's statement of looking for fast calculations. And the statistic we're going to come to, I really thought it was one of the stupidest things I ever heard of, but we have our two sequences, say the same distribution on each one of them, and P sub k is the probability that k random letters match. And the computational efficiency here is that we're just going to count words. We're going to look at the statistics of the words of length k for each sequence and compare those statistics. So linear time in the best sense of linear time. This k is in there. But we're going to multiply the number of times W occurs in A by the number of times W occurs in B and sum over all possible words. That's really looks like a simple statistic. And just to, so normally for alignment, we don't allow these matchings to cross. But in this D2 thing, we allow all possible matchings. So just looking at this, if you can turn that sum of NA and B to a sum of indicator functions, does the word starting at I in the A sequence and the word starting at J in the B sequence, are those K words equal? And 1 if they are and 0 if they aren't. So we've converted it to something that looks like an array of random zeros and ones. Okay. That's what this is, match indicator. And you get the K word matching if K of those on the diagonal are equal. You can compute the mean and the variance and so on. Skip this. Yeah. So here we have these random variables, which are 1 and 0. And if they're independent, you wouldn't need any of us to do that. So if they were independent, there would be approximately normal. The dependence is not too great, and using Stein's method, we expected to get a normal approximation. I'm just going to go through some of the mess. Haiyan Wang was involved with this. We started working on this, and a nice surprise. So this is just used, and we have all these bounds. Here we go. So here's the bound we got, how good our distribution was approximated by the normal, da-da-da-da-da. Looks great, right? The square root of log n divided by the square root of n, da-da-da-da-da. So when alpha is less than a sixth, the error bound goes to 0. You have a normal approximation. So we've got our word size calibrated about right. It's log base 1 over p times t of n, alpha between 0 and 6. So that's great. However, when I was working with us on this, came back and said, it's wrong. And there's something different about the uniform distribution than the non-universe distribution. And I stupidly said, Ross, go check your code. But when you go back here, the probability of 3 letters matching divided by the probability of 2 letters matching squared is 1. So there was a 0 divide in that bound that I kind of blithely went through. So, excuse me, that's, of course, only true for the uniform distribution. And that's where the uniform came in to be a different story. So here's the simplest possible example. You could look at this. We take 1-letter words, so there's none of this overlap nonsense troubling us. 1-letter words, 2-letter alphabet, and the D2 would just be count the number of zeros in one sequence times the number of zeros in the other sequence. And if this is x is the number of zeros in the first sequence, n minus x is the number of ones. So there's our D2. We can calculate it. We can compute the variance. And then suddenly something weird happens. The variance, if p equals q, it's uniformly distributed, the variance is order n squared. If p is not equal to q, the variance is n cubed. Whoa. All my computer science friends always would claim that, you know, it's all just counting and you guys are just doing frills, putting p's and q's on there. But this is really different. Oh, what the heck is going on? So let's do what I tell my freshman statistics students to do. Subtract the mean, divide by the standard deviation. Okay. We do that. We crank along here for a while. And you get 3 terms unless p is a half, p equals q. These guys have disappeared. So what's going on is that these 2 terms are dominating the limit, providing the normal approximation. And this is, in the limit, the product of normals. So these 2 terms dominate this guy. That's where the difference in variance came from. I see it. I still don't sort of have it in my soul. But that's the story. So you would have a normal limit, and you would be checking how well the statistics of the y sequence is doing against the y sequence, how well the x sequence is doing, and the cross product terms are just in lower order and disappeared. So when p is not equal to q, when it's not a uniform distribution, these guys dominate and they tell you very little about what you want to know. That is, are these sequences related? So we have various ways of looking at this. Every statistician does, as I said, subtract the mean. So if we subtract the mean that goes with the word counts and then sum those centered terms, you get somewhere. And if you expand the original D2 into this form, you can sort of see more evidently now what's going on. When it's a uniform distribution, PW, XW, this all adds up to the number of words, which is a constant. So when it's uniform distribution, these guys disappear. They're the ones that making the cubic variance when It's not uniformly distributed. So that's what's going on. And so what we have spent some years doing is subtracting off these kinds of terms and trying to make this work. Just a couple of comments about that. Larry Shep, who was an amazing character, passed away not so long ago. In 1964, he discovered that x and y were independent mean zero normals with their variances, and if you did x times y and divided by the square root of the sum of the squares, you got something normal again. So we like this because it's self-normalized. You don't have to come up with anything out of the blue. There you go. So we hope that would work. And we also used x times y, and this is an approximation of the standard deviation to divide by. There's been a lot of work in this direction. It seems that you give a tremendous amount up when you just do these four-letter word counts, and that you can learn anything from it is pretty cool. And we're using this in metagenomic data, trying to use it to associate viral sequences that are in the whole metagenome with the appropriate bacteria they're infecting and so on. So there's these are actually getting used a lot. So that's where I am. Hopefully I give you a bit of an overview of this area and a couple of simple unsolved problems like Poisson approximation of the whole logarithmic region and the full distribution of the longest common subsequence. Statistics, to me, the statistics and the algorithms are all intertwined with one another, and it's really one subject and not two different ones. Cool. Thanks.
Questions?
Sure.
Not sure I get this, but for the first phase transition diagram you drew when you have delta and then the mu, and at the sharp phase transition, approximately what are the values? It makes me really worried.
So you're asking what part of that curve do I know?
Yeah.
I can try to remember.
Like, are we in the safe realm?
So some of this is let's see. So obviously those 2 points you know something about. So I think this is I can't remember, but this is the delta and this is the mu. So this is the insertion deletion penalty and this is the mismatch penalty. And this is known, and in fact we know this whole line. But what happens on here, and I think we know this line too. So what we know, if I do wiggles on it, I think we probably know that. And I'm not sure if we know where the corner is or not. So it's not a lot. And we were working on this problem, and Richard went on sabbatical. And it came back with the proof these interacting particle guys are very, very strong. And he had this block argument. Came back from sabbatical. He showed me the block argument. It took a whole afternoon. And literally, I had a headache. This was just, and then we found the Azuma-Hefting results so we could prove the phase transition much more easily. So while Azuma-Hefting was useless for p-values for global alignment, it was incredibly useful for giving a result that was very sharp. Excuse me. Hey.
So for the LCS problem, the IID distribution having no bounds. So would anything of the following form be of any use? And you say non-trivial, I don't know what you mean. Let's focus on edit distance and small edit distance. Is anything known for small edit distance? So I'm talking about.
But see, to get the random sequences to be close to one another, you're fiddling with random, right? I mean, that's what Messenger, these guys did. They take one 0-1 sequence, and in the other one they make it very rare, make one of the letters very rare, and that way they can get their hands on it.
Right.
And I think that's the kind of question you're asking.
Yes.
So they have got a couple of really, really interesting technical papers in that direction.
I see. Because there are a bunch of those newer results on embedding edit distance to Hamming distance with logarithmic distortions. So you may be able to drive similar results.
Yeah. I mean, people have been, the 0.82 or whatever the number I put up there is there are some rigorous upper and lower bounds, but there's nothing, nobody can compute. It is alpha equals da da da.
Right.
Pretty cool. Let alone the full distribution. And the guys that I was just referring to, they say something. I mean, they realize that the longest increasing subsequence of a random permutation is related in some way, and they talk about that.
It is, yeah.
It's a good place. It's good. Their paper's a good place to start.
Yeah. In embeddings, for example, there's a gap between the permutations, where you're guaranteed that each symbol appears once and multiple times, and that gap apparently is a fundamental gap.
Apparently, and some smart people have worked on this problem. I would love to see the answer. But it ain't going to be me, but I would love to read your paper.
Okay, so thanks again.